Okay, so thank you all for coming and joining us. After some talks with several people across the different projects that are happening this summer, some of the more senior members of the group came to the realization that there's kind of like a lack of general understanding of vocabulary, mostly because we all come from different backgrounds, which is actually a strength of the group. The diversity of everything that we bring into the table, it's really cool because we can collaborate, bring different perspectives, think of things that people who have been thinking a lot about a certain problem might not be aware of. So diversity is definitely a good thing, but it has a caveat that getting people to be on the same page takes a while. So we wanted to accelerate that process. We wanted to help people who are just joining this group, which is at the core a theoretical chemistry group. Yes, we are venturing, or well, we have been venturing for a while in other areas, but and those areas are actually what have made it appealing to people coming from physics, computer science, and so on. But yeah, we basically want to make sure that everyone has that fundamental understanding of theoretical chemistry. Even over the past few weeks, you have heard how Alan is very adamant to make sure.
That's why I'm here.
that the grad students are masters of these topics. So, okay, unfortunately, this is not geared towards grad students presenting their candidacy exam. This is more kind of like a refresher of some high school concepts in chemistry, but also push them towards the more advanced concepts that hopefully can be useful for you during your stay in our group. Okay, so I certainly hope that this is not me just talking to you. Like I expect you have questions, that whenever something I'm showing something, you raise your hand and say like, I'm not at all familiar with that. So I'm completely willing to elaborate. This is a very long session, but I plan at least one break. So hopefully we don't get burned up a lot. Yeah, so let's get started. Okay, so there are actually several ways of thinking about the problem of electronic structure. If you ask, for instance, Abdul, another senior member in the group, he will tell you that it's kind of like a numerical problem. But I'm gonna give it a different perspective that has more to do with the algebraic part. And to me, the problem of electronic structure narrows down to separability. Now, what do I mean by separability? So let's take this problem of partial differential equations. Is everyone familiar with partial differential equations? So basically, what we want is we want to know what this function is given the structure of a certain operator. A certain operator that it's composed by functions, well, also functions of the same variables and derivatives. And we want to solve this problem where I say this operator acts on a function, and as a result, I get the same function just multiplied by a number. So I'm operating derivatives, and I'm multiplying by things that are also functions, and at the end, I want to just recover the same function with a constant multiply. So this is what's typically known as an eigenvalue problem. Okay, now if you see this this operator, it looks pretty ugly. Do you have any idea how we can solve this equation?
Oh no, like set the theta to 0, so you get like the ones and stuff like that.
Yeah, so you could just see if you're thinking of a like divide and conquer approach. So yeah, so like you solve one part, you solve the other. Okay, Andreas Burger, an ansatz. That's exactly the way to tackle this in a brute force way, let's say. So an ansatz means we propose a function that if we have some intuition or if we have prior knowledge, could be reasonable to tackle this problem. And indeed, I mean, if I propose this as a solution, I give it some degrees of freedom. So in this case, alpha and beta don't appear anywhere in my original equation. So I just hope that by using this suggested form of solution, capital A, alpha, and beta can at the end be adjusted to solve this equation. Okay, so I just plug in these ansatz on both sides of my equation, and then upon performing all the operations, I get to an equation for the constant, and upon applying all my algebraic and trigonometric properties, I get to a constraint on my constant and say, oh, actually this constant is a constant, like it doesn't depend on either r or theta, and I solve my problem. So it turns out that I proposed a good ansatz, and this ansatz solved my equation because I was able to say, as long as I have this relationship between my parameters and they fulfill the requirement of a constant imposed by my initial equation, I'm solving this problem. It turns out that for this specific operator, there's an alternative approach. So if I take a look at it, and very on purpose, I gave the variables r and theta, which reminds us of circles. So we basically have a radius and an angle, right? So let's define Cartesian coordinates that describe a circle. It turns out that if I do this change of variables, the problem simplifies a lot. So the operator just looks like this. And then I can use a different ansatz, and in this case, this ansatz is multiplicative. So you can again plug in the ansatz and apply the operator and see what are the steps that are derived from it, and you get to the exact same result. But there were several things that happened here and that I want to highlight. First, we were able to simplify how the problem looked like by doing what? By acknowledging a symmetry in the problem. So the problem, it turns out, encoded some circular symmetry, and when we realized that we were dealing with circles and we approach it with the right system of coordinates, we were able to make it simpler. But other than that, a very important feature of the structure of this problem is that once we realize that the operator is an addition of operators, each only dependent or in a single variable, then the solution, the function, the eigenfunction, it's a product. So this is how I'm gonna think about separability from now on. Is if I have an operator that is the addition of independent operators, so each component of the operator depends only on a single variable, then the function that solves the eigenvalue problem is a product of functions that are also dependent of only one of the variables. Okay? Okay, now why am I going about this topic? So, oh, sorry. Actually, there's an even or a more general way to look at it. The problem of eigenvalues is not exclusive to differential equations. You can also find it, and actually it originated in linear algebra. So let's say that I have this problem where I want to find the eigenvectors of a matrix. So M and N are matrices, U and V are vectors, and then I have the problem where by applying the matrix or multiplying a matrix times a vector, I get the exact same vector, but just scaled by a constant. And I know that this is true for two vectors. Okay, is this notation clear? Is everyone familiar with linear algebra up to this point?
Operators?
M and N, so in this case are matrices.
Okay.
But it turns out that there's a natural between
Matrix alpha and beta are like constants.
Are numbers.
And U and V are like vectors.
Are vectors.
Okay.
Correct. So yeah, so okay, this is a very interesting mapping that we have to make. It turns out that when you think of functions can be represented as vectors, and operators, which are recipes of what you can do onto a function, that it can be described in the same way in which you describe the multiplication of a matrix to a vector. So because a matrix changes a vector into another vector, that is, abstractly speaking, the same as saying an operator changes a function into another function. So we have kind of this equivalence: vector, function, matrix, operator. Okay? So we have the same problem, just expressed in linear algebra. A matrix times a vector gives us a constant times the same vector. And this is the definition of eigenvectors. So these are the vectors that if you write the matrix in the basis spanned by these vectors, your matrix is going to be diagonal. Okay, but I want to show you a very interesting property. So let's say that we know two matrices or two matrix vector pairs that fulfill an eigenvalue equation. So I can mix the spaces upon which they act, and by that I mean I can create a larger vector space, which is the tensor product. Are you guys familiar with tensor products? No. Okay, very quickly. So let's say that I have a vector that I can write as A1 and A2. And I perform the tensor product with B1 and B2. Then, numerically, this can be computed as just taking this vector and multiplying by each of the elements of the first one. So then I will get A1, B1, A1, B2, A2, B1, A2, B2. And this concept can be extended to vectors, matrices, whatever. But so that's operatively what's happening, but abstractly speaking, what you're doing is you are compacting two spaces such that you only need one object to describe the action of things that operate on those separate spaces. So You can have operators that act on the first space, so you can have operators that only act on A, operators that, or matrices that only act on B, but then you can compact the fact that they are in different, acting on different spaces in the same object. So what I'm saying here in this second line is precisely that. Is I want my matrix M acting, so I is identity matrix. So I want my matrix M to act on the first part of the total space and the N matrix to act on the second part of the product space. And so like you can even, if you distribute this formulation, you get, oh, M is only going to act on U because B is going to be left alone since it's multiplied by I, by the identity. And conversely, then U is going to just multiply the identity, but N is going to multiply B. Right? So that means that these operators are acting on independent subspaces. Okay. So yeah, this is just the natural consequence of what I just said. M acts on U, B is left alone, U is left alone, N acts on B. And what do we get? We get that because we know that this is an eigenvalue problem, we can extract alpha, and B is an eigenvalue problem, we can extract beta, which means at the end, this was also an eigenvalue problem. Now, what is the point of this? The point of this is we recover the exact same structure as I pointed out in the differential equations problem. If you have an operator that can be written as the addition of two operators acting on two different subspaces, the solution, the eigenfunction, is the product of two different vectors, right? So this is just the vector matrix representation of this, okay? Okay, so that's separability. Now, why do I care about separability? Let's talk about the simplest system that we care about in quantum chemistry, the hydrogen atom. So the hydrogen atom requires us, or actually all of quantum mechanics, require us to solve the Schrödinger equation. What is the Schrödinger equation? The Schrödinger equation is an eigenvalue problem, and the eigenvalue problem is applying an operator that we call the Hamiltonian on a function. It should return the energy of the system multiplied by the same function. Okay? Are you familiar with these notations? Are these like bar and angle? Have you dealt with it before? It's just basically an abstraction of what a function is. Because it turns out that when we describe these kind of objects in quantum mechanics, we have a flexibility of having them either as vectors or as functions. So because they're not really any of them, we can write them like this, and then we have more liberty to deal with them. But actually, they also offer a more economical way of writing properties for linear algebra. But the way you should look at them is just as vectors. Okay? So here what I'm saying is I have an operator that is going to modify my function, and as a result, I want a constant that multiplies the same function. Now, why is this important? Why does this have a physical meaning? It's because this operator is the operator that gives me the energy of the system. So in the hydrogen atom, we are describing a proton, which is a positive charged particle, interacting with an electron, a negative charged particle. So the energy, we can just write the energy in the classical physics way, and this will be the kinetic energy of the proton interaction between them. So if you have ever taken a electrostatics class, then you might be you might realize that we're missing some Coulomb constants or permittivities or whatnot. But this Hamiltonian is normalized. So I'm basically making all the constants unity.
I have a question.
Yes.
Why do you not put a little hat on the? Do we have to, or do we not have to?
Okay, formally yes, I should have. I should have. So yes.
It's okay.
Yes.
No,
yeah.
I'm
Basically.
just curious if I do that in my comp exam, are they gonna kill me or?
Okay, you're safer if you do.
Okay, yeah.
You're safer if you do. So yes, if you want to be completely formal, if you want to distinguish between numbers and operators, the operator should have a hat. Or an accent circumflex.
Yeah, exactly.
Okay, but do you remember that I told you that if you acknowledge the symmetry of the problem, you could get an easier version of the problem? So in this case, there is one thing that we can do, and we can group our variables, the coordinate of the proton and the coordinate of the electron, to reformulate the Hamiltonian in these two terms: a term that describes the center of mass and a term that describes the interaction or the distance of a virtual particle of reduced mass. Now, what does this separation amount to? Center of mass basically tells you how the atom as a whole is moving in space, whereas this second term basically describes how the proton and the electron are interacting, and you can neglect the translational motion of the atom. So we got indeed an operator that is the sum of operators that are written in terms of independent variables. So that means that the solution should be the product of a wave function describing the translation and a wave function describing the Coulomb interaction. And in particular, the energies should be the sum. Okay? So let's focus on this part. Let's focus on the part that describes the Coulomb interaction. I'm not going over the whole algebra. That actually, like, if you go to undergraduate classes, that usually takes 2 full lectures. So I'm going to spare you that. But the solution of this eigenvalue problem looks like this: is if you apply this electronic Hamiltonian, so the part of the Hamiltonian that describes the Coulomb interaction, and you apply it to the electronic wave function, what you get is the energy multiplied by functions that depend on the different variables. So our hydrogen atom is a sphere, or we can visualize it as a sphere of the electron rotating around the nucleus. So it's going to have 3 variables. It's going to have the distance, it's going to have this angle, and it's going to have this angle. And it turns out that in the same way that when you solve the eigenvalue problem for matrices, you have a family of vectors, or if you solve the eigenvalue problem for differential equations, you can get a family of functions. That's the exact same thing that happens here. So it turns out that the functions that can solve this eigenvalue equation have labels. So you can enumerate the possible solutions in terms of these subindices, which we call quantum numbers. Now, what do they mean? I'm going to talk about that a little bit later. But something that's really important is that the constant that you get multiplying the wave function is the energy. It's the energy of the nth state. So you have several solutions labeled with different quantum numbers, and to each solution with a given n, you find a different value of the energy. Okay. So if we go into a little bit more detail, how do these functions look like? So we have what's called the radial part of the wave function, and it basically tells you how the electronic density is spread around the nucleus. And then depending on the labels, so you have n, what we call the principal quantum number, and L, that we call the azimuthal quantum number. And this tells you a given distance of the nucleus, how likely it is that you're going to find the distribution of charge, or how intense the distribution of charge, or how, well, depending on who you ask, how likely it is that you find the electron if you probe that region. And this angular part, this is what's called spherical harmonics, and they basically tell you what is the shape of the density around the nucleus. So in particular, if you take the lowest possible values of L and M, this function is a constant, and because you're looking at a spherical function, a constant, that just means you have a sphere. But then as you increase these quantum numbers, you start getting an orientational dependence. So you have things like this, and we call these the p orbitals, we call these the d orbitals, we call these the f orbitals, and they just basically tell you, if you look at the orientation, how is it that you're going to find the electronic distribution around the nucleus. So you have two elements. You have the radial, which tells you what is the intensity as you walk away from the nucleus, and you have the angular part that tells you, okay, depending on what orientation you adopt, how is that density going to be distributed. But there's a little caveat here. So I said that we have a wave function that's a product of functions of different variables, but this doesn't correspond to the same paradigm of separability that I've been talking about. So like in this particular case, it is not true that the energy is the sum of radial plus angular energies. That's not the case, because actually you cannot write this Hamiltonian as the sum of a radial part and an angular part. So this is not what's happening. However, the fact that I was able to separate my wave function in terms of functions that depend on different variables, that's because I was able to acknowledge symmetries. Symmetries in quantum mechanics are encoded in what we call commutators. A commutator is simply when you have two operators. So basically, let me write that. So if you write this thing, and these are two operators or two matrices, all that you're doing is you're writing the subtraction of having them in one order and in the other. But when you have matrices, that subtraction isn't necessarily zero. When you have matrices, you can swap the order in which you multiply them, and you might as well not get a zero. But if it turns out that you can identify operators that commute with the Hamiltonian, then those operators are telling you about the symmetry in the Hamiltonian, and it turns out that you can exploit that symmetry to simplify your problem. So because this Hamiltonian commutes with the operators related to angular momentum, that's why we were able to extract the angular part. Okay. So again, this is I didn't want to go over all the algebra, calculus, blah blah blah. I just wanted to give you the intuition of why the result looks like this. If you want to get more into the what's happening in these wave functions, this is how they actually look like. The radial part, depending on the quantum numbers. But there are some patterns that we can recognize. For instance, they are mostly exponentials that multiply a polynomial. So because of that, we get things that decay as you walk away from the nucleus. But we have, because these are polynomials, you have nodes. So you have some regions or some points where the density is 0. So it's impossible to find an electron at that specific density. At that specific distance. If we look at the orbitals, at the angular part, as I said before, with the lowest quantum numbers, you get a constant. So orientationally speaking, a constant, that just means you have a sphere. If you have this value for the L quantum number, you basically get straight lines. So you have a straight line in X, Y, and Z. So that just means that you confer of a sign. So you say there's one part that's going to be negative, another part that's going to be positive. That depends on the axis that I'm looking towards, and the same can be said for the other functions.
Sorry, Jorge, can you clarify something?
Sure.
So if you try to solve the Schrödinger equation for the hydrogen atom, do you necessarily derive or arrive at the spherical harmonics? Or is there like some choice of other basis functions or representations?
Okay, excellent question. So the hydrogen atom is analytically solvable. That means that all that you need to solve it is a book with properties of differential equations and some other advanced math regarding polynomials, and you can do it with pencil and paper or Mathematica. But precisely the fact that the Hamiltonian commutes with the angular momentum operators, it tells you exactly what is the structure of the wave functions. And it turns out that the eigenfunctions of the angular momentum operator are precisely the spherical harmonics. So these functions y of theta and phi, these are what we call the spherical harmonics. And because these functions are the eigenfunctions of the angular momentum operator, those are the ones that are demanded to solve problems with the spherical symmetry, as in the case of the hydrogen atom.
Can I add maybe something?
Yes.
In the case where you have like a degenerate subspace, you could, in principle, if you do it numerically, get like a random linear combination within that manifold. For example, LZ, you could also choose LX or LY. I think that would maybe.
Yes. Okay. That's a very, very important insight. The spherical harmonics, the way are written in this way, they should be complex functions. But when we have degenerate subspaces, and what do degenerate means? Degenerate means that when you apply an operator to different functions, all these different functions give you back the same eigenvalue. So when you have that case, when several functions give you back the same value, the same constant, then you can actually make linear combinations of the functions in that space and make it simpler for you. So like for instance, yes, these should be, if you write it as spherical harmonics, these should be complex value functions, but the ones that we're plotting here are the real version. So you can take the complex value functions and make linear combinations such that you get a real representation.
Okay, maybe I don't know if this is like, am I tripping or maybe not? Maybe I'm not sure if I follow. But when I look at these, like, I'm just looking at the case of L equal 1, so the first row for the p orbitals, right? There is like colors for like positive and negative, right?
Correct.
And like, I'm just like, just curious, are we taking this coloring thing into account in this equation?
Absolutely.
Oh, okay.
See, yes, because so for instance, when you see this representation of the wave functions,
Yes.
You see that y is going to have negative values for y less than 0 and positive values for y.
Oh, okay, okay.
So you do have a straight line and a straight line that can have negative and positive values.
Okay, so yeah, okay, so the coloring is taken into account because you center it, like you the nodes at 0.
Yes.
Okay, and so I'm just curious about like this, I don't know, this, maybe, are we taking into account the spin and stuff or no? Are we not?
At this point, no.
Okay.
At this
then-
point, no.
And does this have to do with the complex thing you're mentioning or no?
And no,
Not really? Okay.
I mean, because it could also, I guess, happen in case of spin, because if you don't have a magnetic field, you also have like two states and then they have the same energy.
Yeah.
So in principle, you could also combine those and get two new states that are like also eigenstates.
Yeah.
So that would be another example.
Yeah, okay. Like, yeah, okay. Maybe. I don't know, I thought I saw a connection.
It's spin and angular momentum are the same thing, right?
The algebra of spin and the algebra of angular momentum are the same.
Yeah. So that's why maybe you saw.
Yeah. But spin is not a problem for the hydrogen atom.
Yes.
Spin is going to become a problem later.
Yes, yeah. Okay.
Okay. So if you put all of these together, what does it mean? Is we're going to represent the density, the charge density around the nucleus in this way. So if you have s orbitals, they are spherically distributed, and the colors are precisely the sign of the wave function. So yeah, these are the squared values of these plots. So this one, for instance, should be negative here if you don't take the square. So basically, if you have s orbitals that are spherically distributed, you get densities that pretty much look like this. But now, if you have other orientation or other quantum numbers that are not don't correspond to the spherical distribution, then you get a distribution like this. So basically, you multiply this density function times the orientation distribution, and you get densities that look like this. So that's what you're doing. Okay, questions about the hydrogen atom?
Sorry, we don't consider spin because we only have one electron we consider?
Correct.
So do you consider it to be like only spin up, or is it just that the probability of up and down is the same, so you consider it to be the same?
Okay.
Yeah, I think that's exactly what you just said, that when we don't have anything that distinguishes spin up and spin down, there is nothing like spin up and spin down. It's just, in theory, there could be two distinguishable states, but they are not since you don't have a magnetic field. So
Okay. So they're just indistinguishable?
kind of you can label them arbitrarily.
Yeah, I can maybe like clarify that. In principle, your Hamiltonian also has the spin part. It's just that in this particular system, the spin part is kind of also separated from the problem that only includes the nuclei and the other degrees of freedom. So, let me know if I'm wrong, but it feels like you already separated the spin problem as a different problem, and then you're solving just everything that is not spin. And then what you would put later is just to the product of the spin and this part.
Yes.
Like following what you explained about separability.
Yes. So basically, okay. So if we go back, this is what is called the non-relativistic Hamiltonian. So we can include other terms from special relativity, and those will force us to arrive to the definition of spin. But right now, I'm purposefully simplifying the problem, where the hydrogen atom by itself doesn't have spin. So I'm solving a problem that's completely spin independent or spin agnostic. But yes, I mean, technically, you could even argue that you have a spin interaction between the electron and the proton. If you remember, spin is kind of like a way to describe where these entities by themselves are spinning. But at this point, I'm just describing the electron as an independent particle. Now, once we bring more particles into the picture, then we're going to realize that we actually need spin. Okay. Okay, so now let's extend this thing to the next possible system, which is the helium atom. The helium atom is described by the kinetic energy of the nucleus, the kinetic energy of both electrons, the Coulomb interaction, in this case the Coulomb attraction between each of the electrons and the nucleus, and the Coulomb repulsion between the electrons. I can, okay, these are approximate coordinates, but I can make use of the fact that the nucleus is way heavier than the electrons to define an almost separable Hamiltonian, where I can isolate again the center of mass from the Coulomb interactions among particles. So again, I can basically say I can ignore how the atom as a whole is moving, because that's a different problem that I can solve in another way, and just focus on how the electrons are interacting with the nucleus and among themselves. So again, I can separate my Hamiltonian in a center of mass and an electronic part. Okay. So we can recognize several contributions to this electronic Hamiltonian. We can say, okay, we have the interaction or the energy of the first electron, of the second electron, and then the interaction between electrons. But something interesting is that if you look at these blue and orange terms, they are pretty much the same as the electronic Hamiltonian for the hydrogen atom. So it's just the kinetic energy of one electron, its interaction with the nucleus, the kinetic energy of the other electron, its interaction with the nucleus, and then something else. So that means that my helium atom can be regarded, to some extent, as the addition of two hydrogen atoms and something else. But there's a problem. Because they look very much like hydrogen atoms, then you could have the hope that the wave function for the helium atom is close, or you can harness some of the lessons of the hydrogen atom to solve it. So, like, for instance, if we ignore completely this the mixing term, the inter-electronic interaction term, you could write with no problem, because this will be a separable operator. You could write the wave function in this way. You could write the wave function as simply the product of one electron with of a function depending on the coordinates of one electron times the wave function depending on the coordinates on the second electron. Moreover, whenever we propose an ansatz, whenever we propose a solution, we need to make sure that that our solution fulfills all the symmetries encoded in our Hamiltonian. And it turns out that if we define this operator, the operator that exchanges the labels 1 and 2, and we make it commute with the Hamiltonian, we get a 0. So what does that mean? That means that if we enact a swapping of labels on this operator, and you change 1 for 2 and 2 for 1, you get the exact same thing, right? Which is not the same that you would get if you apply that operator, if you swap the coordinates of this product. So that means that you need to do something to this ansatz to make it respect that symmetry. And that can be achieved by basically adding or subtracting the same product, but with the swapped coordinates. So if you propose a solution which is a product of wave functions of different coordinates, you always have to complement it this way so that you acknowledge the symmetry. But there is something else. The spin statistic theorem. This is also a little bit more complicated. Like it has its roots in experimental observations, and if you want a more formal derivation, you have to go to quantum field theory. We're not going to do that. But the consequences are that there are particles that we call bosons. For instance, photons, phonons, vibrations, I think magnons, that fulfill this property that if you enact the exchange operator, you get the exact same thing. But there are also other particles we call fermions, and these comprise electrons, nucleons, and if you enact the exchange operator, you get a negative sign. So that means that by virtue of this spin statistics theorem, if you are describing electrons in an atom, then what you have to choose for this linear combination is a negative sign. So only if you describe this expression as the subtraction of these two products, you get this property. Now, how do we extend it, or how can we write it in a more compact way? We define what's called a Slater determinant. So if you notice, I can just write this guy as a determinant, and if you perform or if you resolve this determinant, you are going to get indeed this form for your wave function. Now here I'm introducing these other variables which become important in order to also fulfill some of the consequences of the spin statistics theorem, and that is that I need to label my electrons by an additional coordinate, and that's the spin coordinate. So in some notation, this sigma can have two values, alpha and beta. Alpha typically means spin up, beta typically means spin down. But the point is, in order for you to get a wave function that looks like this, you need to write a determinant, which is just the determinant of a matrix, of an array, that looks like the two orbitals that you want to have multiplied, also including the spin coordinate. And the way you're going to find these determinants in the literature is with this notation. So basically, you're just going to look at the diagonal of the determinant, and the quantum numbers defining the orbitals in the determinant is what's going to define your what we call spin orbitals. So I changed the Greek letter because psi or phi sometimes is reserved for spatial orbitals, whereas chi is usually what describes the spin orbitals, which is the product between a spatial orbital and a spin component.
Can you repeat that part again?
Yes. So in the literature, you're going to find a psi or phi to describe spatial orbitals, and you're going to find chi to describe spin orbitals. And a spin orbital is the product of a spatial orbital with a spin coordinate or spin function. Okay.
So can you just elucidate why we use the Slater determinant and not our previous notation of just plus minus?
Well, because it encodes it, right? So if you resolve this Slater determinant, you get to this expression.
Right, but why is it more useful to write it as a matrix?
Okay, so in this case, it might not be as obvious because we only have two functions. But if you increase the number of electrons, and if you increase the number of wave functions that you're going to multiply, encoding all the swaps of signs in each of the terms, it's way simpler to write it in a determinant than writing it as a inline function. So a determinant basically takes care of the right distribution of plus and minus signs. Otherwise, you will have to by hand check that the permutations are the correct ones in order for you to get this response. Does that make sense?
Yeah, and so the Slater determinant, it only describes how we basically combine together the individual hydrogen approximations, but not how they interact yet, right?
Yes.
Okay, thanks.
Okay. So now that we have our notation for determinants, this is what helps us define what you're gonna hear named as the electronic configuration. So electronic configuration, it's just basically the notation of all the things that identify the electrons that you are invoking in your wave function. So you need all the quantum numbers that identify a spin orbital. Oh, sorry, I skipped an S prime here. But the point is, each of the spin orbitals has its own family of quantum numbers. So you could just put the quantum numbers instead of the chi. Now, how does this look like? So if I have two, again for the helium atom, I have my two electrons, and I have one, or well, both of my electrons are in the state with principal quantum number 1, and then the angular quantum numbers are 0 and 0, so the azimuthal and magnetic are 0 and 0, so that means they are both in 1s orbitals, but because of the anti-symmetry principle, they need to have opposite spins. So one has spin alpha, the other one has spin beta. But because they are both 1s, then the electronic configuration is 1s squared or 1s2. Now I can describe my second electron as being in an excited state of the hydrogen atom. And here I didn't commit to alpha or beta. Like they could both be spin up, they could both be spin down. That doesn't really matter. But the point is, whenever you have these two electrons, then because you have a 1s electron and a 2s electron, that's how you write your configuration. You can also have one electron with the azimuthal quantum number 1, so then you have a 2s2p, 2p squared, so on. So whenever you see an electronic configuration which is written in this way, 1s, 2s, this is just a compact way of describing the quantum numbers in a determinant. So these determinants make a base, yes? M is the magnetic quantum number. So in the hydrogen atom, okay, so let's go back to the hydrogen atom. So in the hydrogen atom, the spherical harmonics, they also have they have the azimuthal and the magnetic quantum number. And the magnetic quantum number can be regarded as the orientation. So the azimuthal, you can think of it as the shape, and the magnetic is the orientation. So L tells you we have straight lines. M tells you what direction each straight line is pointing to.
Can you explain at which point we get the spin in there? So if you look at the Slater determinant, they already have spin the individual components here, or is it like, do we add it on extra?
Okay, so if we didn't have the spin, if we just plug in this determinant, the spatial orbitals, you will have repeated columns or repeated rows. So that will make the determinant 0. So you need the spin to make sure that the determinant is not 0.
Yeah, okay, that makes sense.
Okay, so the determinants are a basis for the Hamiltonian. What does that mean? That means that if I want to write my Hamiltonian as a matrix, as opposed to as a differential operator, I can use the action of my Hamiltonian on each of these determinants to define matrix elements. So, for instance, I want to act my Hamiltonian on a wave function, and it solves the problem. It solves the eigenvalue problem if I can extract the energy, and this wave function is a linear combination of my basis elements. And this is the method that we call configuration interaction. So basically, I want to use these determinants to actually get the solution of the Schrödinger equation. Now, you could ask, but like, why do I even need to sum over the determinants? Like, aren't these already eigenfunctions of the Hamiltonian? And the thing is, no, they're not. If you evaluate the Hamiltonian, if you try to extract matrix elements from the Hamiltonian, you get, and you use hydrogen spin orbitals, you do get a very important contribution in the diagonal. But you also get a matrix element that is non-diagonal. So, and this non-diagonal, where does it come from? It comes from the repulsion, the interelectronic repulsion. So if my Hamiltonian were just the parts that look like a hydrogen atom, then yes, my determinants will be my actual wave function. But because I have this thing, this additional thing, then it turns out that the determinants are not the wave functions, and I need a linear combination of the determinants if I actually want to diagonalize, if I actually want to find the eigenfunctions of my Hamiltonian. So basically, you can write your Hamiltonian in terms of these determinants, and it will give you some diagonal elements, and it will give you some off-diagonal elements, and then once you write your matrix, you can now use a computer to diagonalize your matrix. So this concept of electronic configurations, it applies further than the helium atom. So if you see a periodic table in any undergrad chemistry classroom or high school chemistry classroom, you're gonna see that the periodic table has these things to describe the atoms. They have the electronic configuration of each atom. But with what we've seen, we now know what this means. The configuration, the electronic configuration, it's just a way to describe the determinant that describes the best solution of the Schrödinger equation, assuming that you ignore all the interelectronic interactions. So if you approximate your atom as just a bunch of hydrogen atoms that don't look at each other, then you get a determinant, but it's an approximation. You're making an approximation that the electrons are not interacting.
So you're writing like the interacting wave function as like a linear combination of non-interacting wave functions?
Yes, exactly.
Sorry. The electron repulsion, is it still there when you do SCF? Or like, what is it? It's like independent electrons, but they all behave as if there is some mean field, and you find this mean field. And so technically it's still there? Or like, is it, because if it was completely gone, then you could just take a product of, is that right? Or
I'm gonna get there.
okay.
Yes.
Can you go back? So you use the linear combinations of
Determinants?
so yeah, S bases to then. So I mean, now these linear combinations can be eigenfunctions.
Correct.
Okay, but the eigenvalues will have these non-diagonal terms. Okay, so the non-interacting orbitals are not eigenfunctions?
Correct. Because
And
this guy.
Okay, and so the bottom line is you apply the Hamiltonian on the function which is not an eigenfunction, and then you get this matrix term. Okay.
Exactly. So if these were eigenfunctions, this term wouldn't exist, and you will have a diagonal. You will have a diagonal that is exactly the sum of the energies of each orbital. Okay?
And you can use it to then diagonalize.
Exactly.
And for larger systems, the diagonalized version probably looks a lot different to the, or how.
Yes.
And this is something you can only do numerically, right?
Correct.
So just wondering, the basis is more of a choice, right? You could actually do a whole bunch of.
Okay, this slide
Yeah.
is only true for hydrogen-like orbitals.
Okay.
That bottom line is
Yeah.
only true if you use solutions of the hydrogen atom as part of your determinant. If you use a different thing, that changes, and I'm going to talk about that.
No, but like I mean, like, can we expand to like? I mean, it's good for most elements, but I was wondering, like, for the CI approach, could you, in principle, pick linear combinations beyond the p orbital to describe? Or maybe I'm misunderstanding.
Well, I mean, the linear combinations span the whole space of orbitals. The whole space of determinants.
Yeah. But like, because I was referring to the basis, right? Like,
These are just examples. In principle, you have an infinite number.
But we could, in principle, have all the, like, go beyond the p orbital. Size of that would influence the accuracy.
Correct.
Okay, so that's essentially, yeah, so that's what I was getting to. And you don't have to stop at 2p.
No, not at all.
Okay, I see.
Yeah, these are just examples.
Okay, yeah, makes
Yeah,
sense.
these are not
But the whole point is you're using, like, what was mentioned earlier, like linear combinations of the determinants.
Correct.
To construct
Yes.
your approximation.
Exactly. So, how does the Hamiltonian look like once you make it a matrix? So in this figure, the things that are empty are the things that can have a value. So yes. So basically, what this means, a matrix, a very sparse matrix that is heavily biased towards the diagonal, and you're going to have also non-diagonal elements, but they're going to have this structure, and I'm gonna detail in a second what these numbers mean. But the point is, the matrix that you have to deal with pretty much looks like this. Okay, now all that I have been discussing so far is in terms of hydrogen orbitals. So solutions to the hydrogen atom wave function. So solutions to the hydrogen atom Schrodinger equation. So that means that we have an exponential, some polynomial on R, this thing called a Laguerre polynomial, and the spherical harmonic. But there are several problems with using this basis set. One of the problems is that in order to get the matrix elements that I'm going to use to numerically solve the problem, I need to perform integrals. I need to act the differential operators in the Hamiltonian on this function, then multiply again by another function, and then perform an integral. So I get rid of the variables. Performing integrals of that kind on functions that look like this, it's very expensive computationally speaking. Not only that, if you want to use these orbitals to describe elements or molecules or whatever chemical entities other than hydrogen, these have a very important limitation. And it's the fact that when you were able to solve the Schrodinger equation and have the quantum numbers, you are describing what's called bound states. You're describing the electrons in different orbitals, the electron in different orbitals interacting with the nucleus, but that it's still bound to revolve around it. There are also other states called non-bound states or states in the continuum, which basically describe a hydrogen atom that's ionized. So you still have a proton, you still have an electron, but they don't really see each other. The electron is just a free wave. When you constrain your space of work to these Laguerre polynomials, you completely neglect the non-bound states. And it turns out that if you want to describe more complicated atoms or more complicated chemical objects, you need information from those non-bound states. So you need to go beyond what's described by these Laguerre polynomials. So what we do is actually we simplify things with things that are dirtier, and because they're dirtier, they have access to that information. And we use, or the first one that were suggested were the Slater orbitals. So these Slater orbitals are interesting or are useful because they preserve the exponential behavior of the wave function, and by virtue of being these polynomials, they can also mimic somehow this polynomial and this polynomial, and also the polynomials in the spherical harmonics. So you can basically just play with these numbers in order to get things that pretty much mimic the behavior of the hydrogen orbitals, but are actually more useful in describing other atoms. But evaluating integrals with this is also expensive. So people have resorted to use Gaussian orbitals. So instead of using an exponential, you use a Gaussian function. And these have the virtue that when you're dealing with Gaussian functions, their integrals are analytical. They are tabulated, and you just need to go to an old book of mathematical functions, and they are there. So because these are analytical and people already know the answer, this saves a lot of computing, but there's a problem. The problem is, if we compare Gaussians with exponentials, we see that the Gaussians fail at reproducing this cusp, and they also fail at reproducing this tail. So what do we do in order to keep the advantage of the analyticity of the Gaussian integrals? We make linear combinations of Gaussians. So we basically try to add as many Gaussians as possible such that we capture the correct physical behavior at the cusp and at the tail. So now, in the language of electronic structure, that means that we have a sum of primitive Gaussians. So primitive functions are the ones that have these parameters defined, and we contract them in order to get a reasonable description. If you want a full catalog of all the basis functions that have been published out there, you can go to this website, the Basis Set Exchange, and they tell you all the different parametrizations of Gaussian and Slater wave functions. So whenever you're running an electronic structure calculation, you have a universe of basis functions to choose from, and these parameters have been curated for different physical problems. Yeah, so we can define which basis sets we're dealing with. And now going back to Andrew's question, we don't need to stop at 2p yet. So I was just giving you some examples. But the thing is, if you solve the Schrödinger equation for the hydrogen atom, it has an infinite number of solutions. So the number of orbitals available is infinite in principle. So that means that the number of matrix elements here is also infinite. So we're not going to deal with infinite matrices. We truncate the basis. We choose what are the orbitals that we're going to consider in order to construct our determinants. And that is what defines this hierarchy of basis sets. So basically, we say CBS. I don't know what that means. So yeah, so you can have minimal basis sets. So that means you take just the number of orbitals required to describe the ground state. You duplicate it, and that defines your whole space. So you're not using infinite. You're using actually the minimal possible number of orbitals that you will need to describe your ground state determinant. And you can grow the number of orbitals available, and as you grow this number of orbitals, your accuracy is going to increase, but at the expense of computational demands. So then it becomes an optimization problem. Is how accurate you want to be requires you to include more basis functions. It requires you to include more orbitals so that you have determinants. But more determinants means a larger matrix, and if you're dealing with a larger matrix, then that means also that you need more computational power. There is also something that you need to be careful when dealing with basis sets. So the hydrogen orbitals, they had the virtue that they were orthonormal. So that means that if you perform the inner product between two orbitals and they are not the same, you get a 0. But that is no longer true. If you use Gaussian orbitals, they are no longer orthonormal. So that means that whenever you formulate a quantum chemical problem, you need to acknowledge the fact that they have some overlap. So that's what this S means. You have a non-zero overlap between non-identical spin orbitals, and that means that the problems that you're going to solve, so like for instance, if you want to write your Hamiltonian for the helium atom, the Hamiltonian now is no longer diagonal. So the hydrogen-like orbitals, they gave us a very pretty diagonal substructure just perturbed by the interaction. But now with Gaussian orbitals, we lost our diagonal, but we gained the fact that the integrals are analytical. So there's a lot of balancing complexities. Okay, so what is the or what we consider solving exactly an electronic structure problem? What we consider solving it exactly is diagonalizing the full Hamiltonian. So we chose a basis. That means we chose a finite set of orbitals, and that finite set of orbitals in turn defined the amount of determinants that we have at our disposal to build our matrix. Now, how do we build this matrix? That's the one that we want to diagonalize. We basically say that we want to write our solution as a full CI, so full configuration interaction. That means we're going to use all the possible determinants. And we're going to work through some, an example of how one kind of looks like. So the full CI, a linear combination of determinants, is the contribution from a reference determinant. By reference, that means the one that describes the ground state, and the possible excitations. So for the carbon atom, let's say that we can describe we can describe all the electrons with the spin up with this determinant. So we have 1s, 2s, and 2p. We know that the electronic configuration of the carbon atom is 1s2, 2s2, 2p2. But we can make use of a symmetry to say whatever happens to the electrons spin alpha is the same of what happens to the electrons with spin beta. So we only need electrons with the spin alpha, and then multiply the answer by 2. So okay, let's just describe our alpha electrons, 1s, 2s, and 2p zeta. This is our reference. This is the ground state, let's say. But now we have to include single excitations. What do single excitations mean? You take, for instance, the 1s electron or the 1s orbital, and you replace it by another orbital that's available. So in the case of carbon, okay, we said that we were going to have 2pz. So that means that we also have available 2px and 2py. So we can replace the 1s orbital by another 2p orbital, or we can replace it by a 3s orbital, by a 3p orbital, and so on. So you take the determinant, you take the orbitals in the ground state determinant, and you replace one of them by another one of the available ones. Okay? And that gives you the space of single excitations. And now you have to do the same for double excitations. What do doubles mean? You take two orbitals and replace these two by two of the available ones. So in the lingo of quantum chemistry, these ones in the reference, we call them occupied orbitals. And the ones that are available outside of the reference, we call them virtual orbitals. So basically, again, singles is replacing one occupied with one virtual. Doubles is replacing two occupieds with two virtuals. And triples is replacing three occupied with three virtuals. And then it turns out that if you want to actually find the wave function that, even with truncation, like I'm not even using the whole space of infinite orbitals, I'm stopping at 3D. If you want to describe the numerically exact solution of my Schrödinger equation, you need the contributions from all the possible determinants that result from these substitutions. So as you can see, this problem, even though it's truncated, it's already a huge problem. Like it explodes combinatorially. So a full configuration interaction gives you the numerically exact answer, but it's a problem so large that we typically never use it. But this is what the exact solution looks like. Okay. So whenever you see a paper talking about a full CI, it's going to probably be very small molecules and with very small basis sets. Okay, so I think this is a good spot to give you guys a break. So let's come back in 10 minutes. By the basis that you choose, exactly.
No matter what basis set you choose, the electron-neutron interactions are
The determinants don't care about that, but then you, yes, the determinants don't care about that. But the fact that your final wave function is a linear combination of the determinants, that's what brings back the information about the electron rotation.
Okay. And then all of your basis sets, like whether it be like Slater or whatever, they're all based off of the hydrogen. They're all like just trying to improve upon this hydrogen.
Yes.
Okay. And then is Slater orthonormal?
I don't remember. I think not. I think not.
So the only one that's orthonormal is
It's hydrogen.
Hydrogen. And then, Oh yeah, what is constraining the hydrogen like basic sets to like this non-bonded state? Is what is it the R? Like what in the setup makes it so that at the end like you can't consider like non-bonded states?
Well, it turns out that you can find. So when you write a Hamiltonian or when you write the differential equation, you get to a point in solving it when you can make the choice of using polynomials, and those polynomials, it turns out that they have a specified degree, and that gives you the Laguerre and spherical harmonics, or you can just use what's called plane waves.
Okay.
And these plane waves, which pretty much describe a free particle, you can accommodate them in a way that still fulfill or there are still solutions to the Schrodinger equation, but they are no longer in the same family of polynomials.
It's like, because I was thinking if you use like an infinitely large R in like,
Well,
wouldn't that be like
no, that's
like kind of like a non-bonded state?
That's interesting because the thing is you have technically an infinite number of bound states.
Oh.
So you can make n infinite.
And they're all bound technically because you still have this like the spherical whatever, so it's still like how can I describe it? Like why are those considered still to be bound states? Like, what's the difference between a bounded and then a non-bounded state?
The way I see it is that the bound state is defined by quantum numbers, whereas or by discrete quantum numbers, whereas a non-bound state is only defined by its momentum.
Non-bounded states don't have discrete.
The bound states have discrete
Levels of
discrete level. Exactly. Exactly. The non-bound states are in the continuum.
Oh, actually, yeah.
Yes.
On that, like the true spectrum of like the actual operator looks like this, and then there's some cutoff, or
Yes.
at which there are just no energy levels, even if you have full untruncated basis set.
Yes.
Okay. But the infinite number is like just in this like interval of real numbers here.
I don't know for sure the answer for that, but I think not. I think that bound states are those with negative energy values, and non-bound states are the one with positive.
Oh, okay. Wait, sorry. There's no maximum.
Okay, so you have a zero. Then everything that's below this number is a bound state, and you can label it with discrete things, and everything above it is a continuum.
Okay. So it's still this kind of okay.
There are some weird systems that have bound states in the continuum, but I don't think that applies to the hydrogen atom.
Okay, I was actually wondering, like, the reason why we include orbitals beyond the reason why we include an occupied orbital, is it statistics, or where does it like come from? So like, why do we need virtual? Because there's always this notion that the more virtual states you include, the more active. That is in my understanding, but I never really understood why that is the case. Sorry.
So that's because of this. So you want your wave function to be an eigenfunction of the operator, right?
Yeah.
If you're just in minimal basis, or rather, if you just include the orbitals that describe a single determinant, then this is not a linear function. You have a single thing. not be the wave function. A single determinant cannot be an eigenfunction of the Hamiltonian. You need several determinants to have this linear combination.
So if we just have one, if we don't even have the linear combination, then it's just, we're just describing the orbital itself, not the whole system.
You're describing,
say like, for example, for, I don't know, for just a carbon atom, if we don't include the 3D orbitals, if we just look at the SMP, like, where is the inaccuracy?
The inaccuracy is the fact that you're always going to have so is that a single determinant? Yeah, it's just that that in the basis of determinants, your Hamiltonian is not diagonal.
Okay.
So a single determinant is not a good description. A single determinant might give you a very dominant element in the diagonal, and that's basically what Hartree Fock and DFT are.
I have to go.
You can't escape these guys. You can't escape things that are out of the diagonal.
For what, sorry?
Wait, but if we include an SMP, we're still doing a linear combination. We're just ignoring the
This
higher
number?
state.
No, this is the number of
We can
things.
still build a linear combination from.
Number of residues, yes. So there will be more atoms.
Okay, the thing is, there are different
on
linear
average.
combinations.
Yeah, it's a lot, but we
There's
can
the linear combination that defines the molecular
basically I
orbitals.
downloaded like this
And
good
then
chunk because I thought
the
that's enough.
molecular
And then
orbitals
actually
define the
the
determinants,
protein that did
and
it
then you make these linear
doing a lot of the
combinations.
heavy
So
lifting
the linear
regarding
combination
stuff.
that gives you
Once
the
I
molecular orbital
download
is
them,
not the linear
it's-
combinations. These are the like linear combinations nested.
They're
Oh, the linear combination of a linear combination.
and I can also
It's a linear combination of products of linear
basically
combinations.
like once
Wait,
I
so
have
the-
this,
the
if you want
A and
like
B.
smaller size chain or bigger, I can
We
we can start with like we can start with like 5 to 50, like so that's quite small, and then increase.
But the point is if
Yeah,
you
so I think
ignore
the first thing we
orbitals
should do
that
is like
this term you can't account
sequence.
for.
We can I don't know. I think it's gonna be hard, but like we
so
can
if
do
you-
like
if
we
you-
can do
if you
sequence to
just get
structure
one,
first, and then
yes. So if
I
you-
think
if
then
you
we can
use
just be like
one,
we can also do unconditional
then
like so
you're
like,
staying
there's a
in
few
this
things we can
state.
do sequence to
And that
structure.
means that you're ignoring
We can
this,
do
but
like
this always
unconditional
exists.
like give me a protein structure,
Wait,
not
so
giving a sequence
by
though,
doing one, you're
because
saying,
that's what
like,
usually
say for example for
people
carbon,
struggle with,
you
right?
have
Like
SP and then
they first
one
design
S,
a
two S,
protein
one
and then
S,
do
one
it.
S,
And then we can do conditioned
But that's
protein
that's
design
our
false,
we already have
like
a
they
linear
did. So
combination.
you can say I want a beta barrel.
And
Like I want
It's
I
just
want
a global feature.
the
yeah,
what
it would
is
be
it-
like oh I want this thing
what
to
is
have like
different
a general
here?
like 3 alpha helices and 2
But we added the
specific,
orbitals.
and then we can try to do
What
that.
what are we
So yeah, I think with the
But I
protein
guess
thing,
other than
like it
just
should be not
expanding
too hard to
the
do.
Yeah.
And to integrate in our thing.
Cool.
Yeah, sorry, I had some. I think I had a lot of
If
fine, I
you-
won't take
if
them
you-
down, but if you use
If
But
you
it's done,
stay with a
it's done.
single
So,
determinant,
like after that,
you're
it
just
should
using
be
this guy.
like
And you're
once I write the
using
script,
energy
then we
is
can
this
just
guy.
tailor it
And that's
to.
it.
wait, but why is adding
Yeah, yeah.
so if we just look at also by a single determinant you mean
I guess what I
just
wanted to talk
one
about in this
electron
meeting is, like,
configuration
it would be
because
good
that's,
for
that's how you can
everyone to,
occupy.
like,
But if you have
try
more
training the model
occupied
themselves,
states, you can have
I'll just
different
share
ways
the
of
results
occupying.
that the model
And that's what actually allows you to write the matrix.
Okay, okay, I see.
Oh yeah,
It generates transition states and generates just
Yes,
transition
so
states.
you're
have
using
some,
one
like,
determinant,
small-
I
you are
shared just
constrained
the
to
transition
this
states.
cell.
Oh, okay.
And that's it.
So you were happy that already
The
was
energy of
working
my
something else,
system
right? And then
is this guy, and that's it.
One model that does
So
both.
you're ignoring everything else.
But in reality, like if we want to give it physical interpretation.
wait, sorry. What you shared was like it was just
It's
trained
just,
on.
just trained on
Can
two
have
energies,
Yeah,
these
okay.
energies they could excite.
Okay.
That's
Yeah.
how we
So
can
would you want me to
account for the
like for
higher
next week?
ones.
I can first have the
Could
data
that be a
ready, and then
physical
I can do what I can do is
Why
like do
we
a
need-
smaller size because
Yeah,
just as a trial,
yeah.
like
It's
peptides.
like less than 500 or less than 1,000.
Okay, so the thing is,
Okay.
is the
we can
picture
say
of
that our first set
orbitals
of experiments is a
is-
context size of
believing
1024.
that describing
the sequence might be.
the describing atoms with multiple electrons is the same as describing multiple
It's
hydrogen.
okay if there's no hydrogen.
And that's not true.
Yeah, that's fine.
It's an useful approximation
I don't
that
think
gives us a
this
framework
takes in
to
a
calculate
hydrogen
things.
Okay.
Um,
And then
So,
But you would
the
want
thing
me to
is,
do it
when you
only
look
on
at the
this, right?
problem
Like
from the
not
perspective of a
multitask.
many
Yeah,
body
just try it for single task
system,
and then
like load the data and try to see if it
thinking
does it.
about
Yeah,
electrons
like the
jumping
data
into
set,
orbitals, that
you should
becomes
be able to just
an
bring it at the
inaccurate
end.
Oh, yes.
thing.
Yeah, yeah, yeah.
Do everything.
Yeah, okay. Yeah, sorry I have to go. But hopefully like I think I took a look already at how protein and those things and it seemed okay, except I remember then there was a centering.
But those only
that,
good for the hydrogen
it's just like a translation, right?
Yeah.
But if
We
you
have
put those
code.
orbitals for a
exactly.
different
Okay,
helium,
that's it.
then those might be
Oh,
actually.
Oh, because you put it together
so
then, okay.
I don't know if anyone is taking
that's true.
notes,
They are
but if there's
excited only
anything
for
I will
related.
give it
for the
deeper.
hydrogen. they
But
are
when you put it
hydrogen.
together, they might be relevant. Or,
Yeah, and then they are
okay, yeah, that makes a lot of sense.
Always
Cool,
so
cool.
long.
Right. Thanks.
Yeah, it's nice. I actually.
Yeah, I
it
think
was-
the
it was-
mathematical
it was like-
explanation that you're
I
doing,
bought this
it makes sense too.
extension.
Thanks.
Yeah.
Okay, so let's see what else we can get covered in 20 minutes. Okay, so now let's talk about molecular orbitals. I talked about the hydrogen atom and how to construct full configuration interaction with hydrogen orbitals because it's like a good gateway to that. But it turns out that we never use hydrogen orbitals. We use other things. We use what's called molecular orbitals. And what are they? So let's now, instead of thinking about the helium atom, let's jump to the next problem in complexity, which will be the hydrogen molecule. The hydrogen molecule is now described by the kinetic energy of each of the nuclei, the repulsion of the nuclei, the kinetic energy of each of the electrons, and then the interactions among electrons and between electrons and nuclei. We can separate conceptually these contributions. And now, as you can see, the separation is not formal. Like I cannot just simply isolate the coordinates of the nuclei and the coordinates of the electrons and then describe a center of mass in the same way. So to deal with molecular systems, we actually have to resort to a more sophisticated concept, which is the Born-Oppenheimer approximation. And the Born-Oppenheimer approximation, I think Juan is going to talk about it in his tutorial. But the idea for us is that we kind of like freeze the nuclei, and because we're freezing the nuclei, we only care about the electrons. So we no longer care about the coordinates of the nuclei as variables in our wave function. They are just parameters. What does that mean? That means that our electronic wave functions are going to be subject to fixed values of the nuclear positions, of the nuclear coordinates. So yeah, so basically the nuclear coordinates are just no longer variables. They are things that define what is the space of electronic wave functions that we're going to be dealing with. So a little bit of a recap. We said that the wave function is a linear combination of determinants. And in each determinant, what we have is a spin orbital, where a spin orbital is the product of a spatial orbital and a spin coordinate. But now, it turns out that this spatial orbital is not going to be a hydrogen-like wave function, is what we're going to call a molecular orbital. So that means that we're going to have another linear combination inside of this linear combination. Why are we doing that? Because this gives us both a physical insight into the system and also a numerical advantage. What is the physical insight? So again, let's talk about the hydrogen molecule. If we start describing each electron as a 1s orbital, or a 1s electron, it turns out that I can now define a change of basis where two atomic orbitals become two molecular orbitals. So I can just get the addition of these two atomic orbitals and the subtraction. And if I get the addition, I get this new cloud, this new distribution of electronic density that revolves around both of the nuclei. And again, because I started with 2, I need to end up with 2. And the subtraction gives me this thing that looks pretty much like a p orbital. And what's the physical insight that I gain by doing this? By doing this, I basically say that my electron density, it's actually something that glues these electrons. So now I say that I have a charge density revolving around both nuclei at the same time. So I'm basically forsaking the picture of electrons around separate nuclei and going to a description of electrons as part of the molecule as a whole. So for more complicated systems, this is what molecular orbitals look like. So again, if I start with s orbitals, I get this extended thing. So I started with 2 spheres, and now I have this ellipsoid thing. I call this a sigma bonding orbital. But if I subtract orbitals, that means that I introduce a change of sign in my electronic density. So this becomes an anti-bonding orbital. And now I can mix, let's say, p orbitals. And when this mixing is such that we have the same sign of the density revolving around the 2 nuclei, we still have a sigma bonding orbital or a sigma anti-bonding when you have, again, a change of sign. And then you have pi orbitals, pi bonding orbitals, and pi anti-bonding orbitals. So the difference between a bonding and an anti-bonding is whether the density is covering an area with several nuclei, or whether the density introduces nodes, introduces sign flips in between the nuclei. So when you have nodes, that basically that is telling you that the density must be interrupted, and therefore that's like a way to break a bond, so to speak. Now, for instance, in the benzene molecule, this is how the molecular orbitals look like. So you have the pi molecular orbitals, you have these bonding orbitals, and you have these anti-bonding orbitals, and then when you distribute in energy the available electrons, you see that all the electrons end up in the bonding orbitals, and therefore the molecule is stable. Okay, so that's kind of like the physical meaning, but what is the numerical meaning? So the molecular orbitals are linear combinations of atomic orbitals. So what we want is to find linear combination of atomic orbitals to describe the system in the most accurate way. What does that mean? That means that we want to find the best possible single determinant to describe the system. So the molecular orbitals are also framed in a way that they help you to get the best possible physical description within the independent particle approximation. What is the independent particle approximation? Is this thing where we approximate the electrons so that they don't see one another. So that we just have nuclei and electrons interacting with directly with the nuclei, but the electrons don't really see each other. And also, it turns out that if we find this determinant, this good determinant, this makes it easier to solve the configuration interaction problem. So if we use a determinant for which the orbitals have been optimized, the configuration interaction is also going to be simpler. So the matrix that we have to solve is also going to be better behaved. Yeah, and also for other methods that are more advanced, having this optimized determinant is going to help. How do we find this determinant? For that, we use the variational principle. This is actually one of my favorite proofs of quantum mechanics. The variational principle basically says that if your wave function can be expanded as a linear combination of a basis, then okay, you have an ansatz. You propose a wave function and you expand it in the basis of eigenfunctions of your Hamiltonian. So when you apply your Hamiltonian to your ansatz wave function, you basically extract the energy from each of the eigenfunctions. And then if you apply the same ansatz before the Hamiltonian, you premultiply, and you're also dealing with orthonormal basis, you basically get to the point where you have the sum of all the energies multiplied by some positive quantity. So that means that whatever trial function you're using, it doesn't matter which is, the energy that you get from this trial wave function is always going to be larger than the energy of the ground state. So that means that if you can parameterize your ansatz and then turn this problem into an optimization problem, and you minimize the energy as a function of your parameters, that minimal energy that you're finding is the best possible energy that you can have with your trial wave function. So that's what helps us in defining the method of Hartree Fock. So we write for the ground state Hamiltonian, we write the matrix element, and the matrix element, it depends on these integrals. We call this the Coulomb integral and the exchange integral. And what we want is, if we define our molecular orbitals as linear combinations of our atomic orbitals, we want to find what are the coefficients of the atomic orbitals that minimize this matrix element. Why? Because this matrix element is the energy of the Hamiltonian if you assume that the system is fully described by a single determinant. So this is the problem that Hartree Fock solves. The Hartree Fock solves what is the minimum energy or what is the minimum possible value for this matrix element. You want to find what is the determinant, what is the linear combination of atomic orbitals that give you the least possible value for this matrix element. And it does that by finding the molecular orbitals. So the molecular orbitals are the linear combinations that optimize or that solve this optimization problem. With more algebraic details, you basically write a Lagrangian, because this is an optimization problem. So you want to minimize the energy subject to the constraint that the molecular orbitals should be orthonormal, and that basically translates into another eigenvalue problem. But what's interesting is that just by working the algebra of this Lagrangian, you get into a Hamiltonian that doesn't act on the determinants, it acts on the spatial orbitals. So you have this F, we call it the Fock Hamiltonian or the Fock operator, and this Fock operator is diagonalized not in the basis of determinants, but in the basis of molecular orbitals. So you solve the problem of diagonalizing the Fock operator, again, because the atomic orbitals are not orthonormal. You need to acknowledge the overlap matrix. But when you diagonalize the Fock operator, its eigenvectors or its eigenfunctions are the molecular orbitals, and the eigenvalues are the energies of the molecular orbitals. Okay, questions about Hartree Fock?
As the atomic orbitals, you can now either use the hydrogen atom orbitals or the approximations we did.
We typically use the Gaussian ones, the Gaussian orbitals. Yes. Precisely because we need to evaluate these integrals. And these integrals, we know them for Gaussians, and if we want to use other functions, then we have to compute them numerically, and that's very expensive. So, okay, if there's any takeaway from this slide, is that Hartree Fock gives you the best possible single determinant to describe the system. As we said before, a single determinant is not enough. A single determinant is just an approximation, and what you actually need is a linear combination of several configurations. I'm using configuration and determinant interchangeable, but Hartree Fock is given a configuration, it tries to find the molecular orbitals, the best molecular orbitals that minimize the energy for that single determinant. And then dealing with that single determinant is way simpler. Now, if we go back to the full Hamiltonian, to how it looks like, Hartree Fock is basically trying to condition this matrix such that the matrix element here is the largest possible. Such that almost all the matrix is concentrated here. Now, we know that we still have to really deal with the matrix and diagonalize it and whatnot, but Hartree Fock makes its best effort so that you can describe the system just by this element. But depending on the complexity of the chemical system, Hartree Fock is limited, and you have to use post-Hartree Fock methods. Okay. Now, another way to go around the limitations of Hartree Fock is cheating. And that is DFT. So the DFT, density functional theory. So you want to solve the Schrödinger equation. You want to describe kinetic potential energy applied to a wave function, and in a way that gives you the energy back. But the one thing here, or one thing that we have seen, is that the wave function depends on the coordinates of all the electrons, right? But we can define a quantity called the electron density that doesn't depend on the coordinates of all of them, but rather on spatial coordinates in the atom. So what does that mean, or our molecule? So in our molecule, let's say that we just probe one point in space. We don't know what electrons might be contributing, but the point is, because we are standing at a specific coordinate, we can feel the effect of several electrons. We don't know which electrons they are, but at that specific point in space, we feel whatever they're doing to us. So that means that we can define this object called density that it doesn't know about the coordinates of all the electrons, but it knows about the single coordinate at which you are standing in your molecule. And it turns out that you can write your wave function as a functional of this electron density. And because that's the case, you can write your energy also as a functional of this electron density. Now, it has been proved that if this functional were known, the problem will be solved. But no one has found the right way to write this functional. So there are several strategies to try to approximate it. And what's interesting is that we started by trying to distance ourselves from the picture of independent orbitals. So just to capture everything for what would happen at a single coordinate. But now we're going back to the orbitals in order to assemble this object. And what we're going to do is we're going to write the potential energy as the actual potential energy in the Hamiltonian, and also some other terms that should be included in the expression of this functional. But we don't really know how they look like. We just know some of the mathematical properties that they should fulfill. So we write this other term called the exchange correlation term, which basically we tailor to each physical problem so that it gives us the best energy for that specific physical problem. So basically, we take a larger or some source of information. It could be experimental information. It could be a post-Hartree Fock method. So it could be a configuration interaction solution, whatever. And then we see what mathematical structure we need to give to this guy in order to replicate those experimental or more theoretically expensive values of the energy. So DFT is essentially just another version of Hartree Fock. DFT is also an independent particle scheme, but what DFT does is it replaces the Hamiltonian, it replaces the true Hamiltonian of the molecule by a fake Hamiltonian. But this is a fake Hamiltonian that is tailored to capture the interactions across or among electrons that are not captured by Hartree Fock that help in getting good energies or good observables for specific physical problems. And there is a universe of functionals precisely because it turns out that each different physical problem has required a different form of the functional. So yeah, so this is my quantum chemistry snapshot. When you have a Hamiltonian, the information that you have from it are the 1 electron and the 2 electron integrals. By 1 electron, I mean the interactions between electrons and nuclei, and the 2 electron integrals, which are the electron repulsions among electrons. You can use Hartree Fock to define molecular orbitals. DFT also will give you molecular orbitals, but these are molecular orbitals that are ad hoc for a variety of physical problems. And if you have a more accurate description, you require to use post-Hartree Fock methods, which imply the excitation amplitudes. So they imply invoking the singles and doubles and triple substitutions that we were talking about. Okay, and with that, the tutorial is over.
Back on the DFT slide, like, can you explain the functional in those third and fourth line? Like, what's the specific for functional, like the definition of it? Back on the DFT slide.
Yes, give me 1 second.
Maybe in the meantime, as some of you might leave before questions, and so I will try to give a second part of sort of this tutorial, more focused on molecules and molecular dynamics and molecular structure, more than just electronic structure, based on what Jorge already did. And I'm planning to have that for probably this time next week. Seems good, right? But I'll post a similar survey. Yeah, I want to meet.
Okay.
And I'll send the link, and then you guys choose.
If you're here for Pluma, we'll go to another room right now.
So the energy as a functional, you mean?
Yeah.
What is the structure of the energy as a functional? Okay, being completely honest, I am not a DFT expert. So I have the intuition that you add a term to the potential energy, and this term is typically made from the densities, so another function of the density and its derivatives. Because if you want to capture physical effects of the density of how you feel embedded in the field of electrons, you not only need you not only need the intensity of the density, you also need the forces that it induces. So you typically need the density, and you also need the gradient and the Hessian, and some derivatives. But what people do is they tailor different forms of combining the densities and its derivatives in order to capture some physical phenomenon. Thank you. Of course. Well, I hope this was helpful.
Yeah.
Also, you're trying to condense an entire advanced quantum chemistry class in 2 hours.
Yes.
Yeah. For people with most likely not the entire required background. So I think it's,
I was gonna say, I did second, third year quantum, and half of the stuff we didn't do.
yeah,
So I
it is
don't know.
advanced. It's the advanced part of the class, not even quantum chemistry.
I think this covered 2 years of 2 courses of quantum.
covers
And
by, like,
and beyond,
the end
because
of the second year of
the
quantum.
full CI was